In this session, we will talk about the Newton's law of cooling. Let's look at the model. That means Newton's law of cooling assumes that the rate of cooling is proportional to the temperature difference, Y minus T sub A. That means it's not just proportional to the temperature itself, but to the difference. T sub A is the ambient temperature, the surrounding temperature, which will give us some limitation if the cooling off process or warming up process will take place. And this is the differential equation. That's the model that represents this situation. We may notice the rate of change of Y is proportional, K, constant of proportionality, the cooling constant, to that difference, not only to Y, but to the difference. And that means Y is the temperature of the object, hot or cold, actually. T sub A is the ambient temperature, and K is the cooling constant. And in the previous video, we did solve this equation. It's a nice separable differential equation. We can solve it and get this solution. Y equals to T sub A, the surrounding temperature, plus a constant times E to the negative KT. And usually we will say this, but if the constant, of course, could be positive, negative, but if the constant is positive, the cooling off situation is taking place. If the constant is negative, warming up. That means from the object being like colder than the surrounding temperature, the object will actually warm up. Okay, that means now let's look at the couple of questions. What we will need, yes, I will not solve explicitly this equation, but we will need to know the equation and the solution. And then we will look at all of the other components of this equation. Okay, let's see. Exercise number 1. A hot metal bar with a cooling constant, K equals to 2.1 per minute, because 2.1 units per minute, is submerged in the large tank of water held at the temperature 10 Celsius degree. Let T sub A, of course, let Y of T be a bar's temperature at the time T in minutes. A, find the differential equation satisfied by Y of T and find its general solution. That's mean we know, but we have to find exact values. Then B, what is the bar's temperature after 1 minute if its initial temperature was 180 Celsius degree? And part C is asking what was the bar's initial temperature if it cooled to 80 degrees in 30 seconds. 30 seconds, we have to be careful because everything is in minute, and 30 seconds is half of the minute. So let's maybe put it 1/2 of the minute. This will be the time that we're looking for. Okay, and as I said, we have to know this model, this differential equation, dy dt, the rate of change of y with respect to time, equals to negative k times y minus t sub a. And the general solution is this. T sub a plus constant e to the negative kt. We have all of the description, and now let's start. That's mean what we know. We definitely know K, beautiful, and we know surrounding. Okay, that's mean A is that's the differential equation, of course, and the solution is surrounding, which is T sub A 10 plus the constant e to the negative, because we do have negative in the solution, negative 2.1 t. Okay, so that's actually, we don't know the constant because the constant will change. Part A and part B will have a different constant because part A asks for the general solution. General solution contains C, constant C. Okay, part B. What is the bar's temperature after 1 minute? If its initial temperature was 180. That's we know that the initial at time 0 was 180. Okay, that means that's first of all, we have to find a constant. That means let's see, 10 plus C e to the negative 2.1 t equals to 180. Let's maybe correct this a little bit because that's not negative 2.1 t, 180. And actually one more thing, this is supposed to be 0 because it's at time 0. Okay, that means we can see that we will have 10 plus C equals to 180, C equals to 170. Beautiful. That means C equals to 170. And we would like to find out what is the bar's temperature at 1 minute. That means let's see. Ambient temperature, constant, e to the power of negative 2.1 times 1, because time is 1. Okay, and of course times 1, we don't even have to put this. Maybe let me keep it because then we will know. And when we at the test, when we're not using calculators, this is perfectly fine, but let's maybe use the calculator. And I did use the calculator and got 30.82 Celsius degree. That means what is the bar's temperature after 1 minute? Almost 31. 30.82 Celsius degree. Okay, that means that's part B. And then part C. Part C is asking what was the bar's initial temperature. That's when we're looking for the initial temperature. What is the temperature at 0? However, we have different. We have to be careful. I cannot use the equation with the constant from the part B because different situation. If it cooled to 80 degrees in 30 seconds, that means in 30 seconds, half of the minute equals to 80, not 180. Okay, equals to 80. Okay, that means let's do it. General solution, because I use general solution here, and I will use general solution for this one. Actually, that was correct. Okay, that means let's see, 10 plus constant e to the negative 2.1 times 1/2 equals to 180. C e to the 2.1 times 1/2, it will be 1.05, of course, negative. Subtracting 10 from both sides, and then C equals to, when we divide, we will have 70 divided by e to the negative 0.5, but without the negative, we can rewrite as a product. And again, if this will be the exam type, you can leave it like this, but we will use the calculator, and this is around 200 degrees. Okay, 200 Celsius degrees. Okay, that's what we know. We know that our model is y of t equals to 10 plus 200 e to the power of negative 2.1 t. Now t at 0 is 10 plus 200 e to the power of 0, 210 Celsius degree. This is the answer for part C. Beautiful. As we can see, we have to know the Newton's law of cooling equation and the general solution. And then it's easy to decode. Okay, another one. Beautiful. Okay, Bob's car engine runs at 90 degrees Celsius degrees. On a day when the outside temperature is 20 degrees, he runs off the ignition and notes that 5 minutes later, the engine has cooled down to 60 degrees. Determine the engine's cooling constant K. What is the formula for the general solution? Or maybe not even the general solution, the exact solution, the initial value solution, meaning that the constant C must be calculated. And part C is asking when will the engine cool to 30 degrees Celsius. Okay, that's what we know. We definitely know that Bob's car engine runs at 90. That means this is 0. initial value. Y at 0 equals to, we can say Y at 0 equals to 90 Celsius. And we also know on that day when the outside temperature, ambient temperature, 20, okay? He runs off the ignition and noted that 5 minutes later, time is in 5, the engine cools to 60. That's mean Y at 5 equals to 60. We have a system of two equations with two unknowns, then we can try to solve it. Okay, that means the equation will have, maybe I can write here, the equation is ambient temperature, constant, e to the power of negative kT. And we need to calculate constant and the cooling constant. Okay, 20 plus the constant, e to the power of 0, because the time is 0, equals to 90. 20 plus the constant, e to the power of negative 5 times k, because 5 minutes, equals to 60. Of course, the first equation will tell us the constant. Correct? Constant is, because e to the power of 0 is 1, 90 minus 20, 70. And then hopefully we can get constant k. It means if c is 70, I can use it. 70 e to the negative 5k equals to 40. E to the negative 5k equals to 40 over 70. I can simplify to this. And now negative 5k equals to natural log of 4 over 7. If we have natural log of a number less than 1, still positive, but less than 1, this number is negative. And that means I will really recommend rewriting this. Let's maybe use some, okay, that's mean negative 5k equals to, and what we can do, we can also switch that 4 over 7 as a 7 over 4. When we switch it, we know that we can put, it will result in the negative sign in front of this, 7 over 4, okay? And now 5k equals to natural log of 7 over 4. 7 over 4 is greater than 1, that means everything is positive. It's natural log, because I will recommend rewriting this k without a negative sign, because we have to put that k to the general solution, and please notice, general solution includes negative. And that we have to be careful. That means this will be the answer for the test, but since we practicing, we have calculators. Using the calculators, this is the number 0.112 per second. Okay, I mean the equation determine the constant. That means the constant k, maybe we can do here 0.112 per second, and the formula is, let's write down, ambient temperature plus the constant 70. Always from here we can get constant. And k is, okay, beautiful, 70 e to the power of negative 0.112 time. I think I'm like, okay, that's part B. And now part C, what we want, when will the engine cool to 30? We just want to take this equation and say equals to 30. 20 plus 70 e to the negative 0.112 time equals to 30. Probably you know me by this time. We have to align equal sign. Okay, it means e to the power of negative 0.112t. 30 minus 20 is 10. 10 divided by 70 is 1/7. And again, this number may not is less than 1. That we will have negative 0.112 natural log of 1/7. 1/7 is negative. That means let's do this and change for 7. Time is natural log of 7 actually over k. This is the time for the test, but on the written homework or on the practice, we can use calculator, 17.4 minutes. Okay, beautiful. That means it will take 17.4 minutes to cool down to 30. And it's cooling down. We can see the constant is positive. Okay, exercise number 3. Let's see what we have. Frank's automobile engine runs at 100 Celsius degree. One day when the outside temperature is 19 Celsius degree, not that cold, he turns off the ignition and notes that 5 minutes later the engine cooled to 90. When will the engine cool to 40? Similar, yes, we can see similar situation. That's in what we know. We definitely know the ambient temperature is 90. I mean, first of all, engine runs at 100. That means at the beginning is 100. Ambient temperature is 90. And 5 minutes later, it's 90. The same thing. That's when you can probably even pause the video now and try to do it on your own. Let's get an equation and then let's find the when will the engine cool to 40. We definitely need the equation first. Not only the general solution, but we need constant and k. And then we can solve it for time at 40. Okay, that means system of two equations. Y at 0 equals to 100, y at 5 equals to 90. And the equation is ambient temperature. I will just, use the general solution. Ambient temperature is 90 plus the constant e to the negative k times 0, and then 90 plus constant e to the power of negative 5k equals to 90. Beautiful. Okay, what is constant? Constant, we can actually say right away, and this one will give us k. A constant is e to the power of 0 is 1, just 100 minus 19. 81? Okay, that's mean 19 plus 81 e to the negative 5k equals to 90. E to the negative 5k equals to, now let's do the math. 90 minus 19 is, I believe, 71 all over 81. And again, this number is less than 1. That means we will have negative 5k equals to natural log 71 over 81. But we will divide by, I cannot write 2. Let me write, okay. Actually, I can say here, let's say k equals to, okay, natural log, and please notice I will flip this number. This will give me negative in front, but I will divide by, instead of doing like this, dividing by negative 5, they will cancel out. And now we know that this is positive number. And this is good answer for the test. But if we are here now, we have access to calculator. That number is 0.026 per second. Okay, that means that's the cooling constant. Now the equation is not the general solution, the exact solution in initial value. Ambient temperature, 19, constant, and then cooling constant. Beautiful. This is the general solution. And now we want this to be equal 40. What time? Okay, that means the part that actually, because we need this, now we can solve this equation. We can say, oh, how I can write nicely. We want this to be equal 40. What time? That's, we can say 19 plus 81 e to the negative 0.02060 equals to 40. Okay, then e to the negative 0.02060 equals to, again, math, 40 minus 19, 21, divided by 81. Oh, this one we can divide by 3. 7, 27, and that's it. Again, it's number less than. Oh, I don't wanna, let me see what we can do. We can say negative 0.02060 equals to natural log of 7 over 27. And time equals to, again, divide, I will divide by negative, but everything will be positive because I will change this logarithm 27 over 7. Okay, and this is a good answer for your test, no calculator, but when we use the calculator, the time is, and I can maybe write here, approximately 51 minutes. Okay, but please note, natural log of 27 over 7. I flip this negative, and then I reduce that negative. Okay, I have 2 more. You may pause the video, you can come back later, or you can even try to do it on your own, on practice. Okay, it's me now. Let's see. I have exercise number 4, exercise number 5, and we will be done. But you can make a break. You can make a break. Yeah, you will have a good practice. Okay, exercise number 4. Objects A and B are placed in a warm bath at the temperature T sub 0, 50 Celsius degrees. Actually, I would say S or A, surrounding, because T sub 0 is a little bit confusing. Yes, it's not the initial temperature, it's the surrounding. Object A has an initial temperature Y at 0, negative 40. Ooh. And the cooling constant 0.005 per second. Object B has an initial temperature 10 degrees Celsius and cooling constant 0.003 per second. After how many seconds will the objects, A and B, of course, have the same temperature? Interesting. That's mean we have to do it. Basically, what we have to solve it, we have to solve this equation, y at t for the objects A equals to y at t for the objects B, but we need these equations, okay? I can maybe use the sub, let's just see, for the objects A and for the objects B. Okay, that's me first of all, for the objects A, we know the equation. Oh, I didn't type the equation, but let's see. Okay, I can actually say ambient temperature constant e to the negative kt. That means what we know. We know that the ambient temperature is the same for all of them. And then constant e to the negative 0.005 time. Okay, that's the equation. What is the constant and what is the t? We also know, let's see, at 0 is negative 40, yes, the initial temperature. That's, we can say 50 plus constant e to the power of 0, negative 40. Constant is actually, negative 90 Celsius. That's, we have constant. And now, okay, that's it. We just need constant because we do have a cooling constant. Okay. Okay, that's mean the first equation, that's mean this is for object A. Yeah. Now for the object B, maybe a little bit faster because we know the equation for the object B is 50 plus the constant e to the negative 0.003 time. And the initial temperature is 10. That's we will have 50 plus constant e to the power of 0 is 10 Celsius. Constant is e to the 0 is 1, negative 40. Okay, that's we have the equation. For the object A, the equation, yes, the equation for that situation is 50 minus 90 e to the negative 0.005 time equals to 50 minus 40. Negative, that means the warming up situation is. Yes, because we can see how low are the initial temperature and the surrounding is 50. Negative 0.003 time. Okay, subtracting 50 and then dividing both sides. How I can do it? Dividing both sides of the equation by e to the negative 0.003 time and also dividing both sides by negative 90. Okay, when we dividing the same base, we may subtract. That means subtracting negative 0.003, we will be adding. That means this is this, okay, and time. And this is 4/9, if I'm not mistaken. That means we do have e to the negative 0.00249. Negative 0.002 time equals to natural log of 4/9 again. Let's make it positive, maybe this way, and changing 9/4, okay, because that's the same but negative. And then time is natural log of 9/4 over k. Yeah, usually is, yes, over k. And we can leave it like this for the test, or when we actually have access to the calculator, this will be bigger number, yes, because if the denominator is small, the whole number is big. We remember this. It's 405.5 seconds. 60 seconds in a minute. That means this dividing by 66, 36, and 45. That means 6 minutes and 45 seconds. 45 sounds like 70, like 3/4. I don't know if I can write this way, but yeah, units. 405.5 seconds. But I change it for minutes, 6 and 3/4 of the minute. 6 minutes and 3/4, 6.75. Okay, and then one more. Again, you may do the break, yes, or you can pause the video, maybe have a little bit of tea or coffee, and let's try to solve this question on your own, okay? Because the final answer, yes, don't listen what I'm doing, but the final answer is interesting. Let's see if you can get, if you paying attention to all of the details, okay? Exactly what is the question asking, and if you can get correct final answer. I will ask you later. Okay. A hard-boiled egg of 98 Celsius degree is put in a sink of 18 Celsius degree water. That means we can see the surrounding or the ambient temperature is 18. After 5 minutes, the egg's temperature is 38 Celsius. How much longer will it take the egg to reach 20? Okay, that means the initial temperature, I like to say not T, I mean, we can say T sub 0, but I like to say Y at 0 is 98. And then we also know that Y, yeah, let's be consistent, Y at 0, and Y after 5 minutes is 38. We can see almost the same situation. We have the equation Y at 0 is 98. Y at 5 is actually 38. Let's solve it. That means ambient temperature is 18 plus the constant e to the power of, we don't have k. Okay, negative k times 0 equals to 98. That means 18 plus the constant, 98. Constant equals to 80. Nice. We do have constant. Now let's use the other equation. That means this will give us constant. And from this one, we will get the cooling constant. Yes, the arbitrary constant and the cooling constant. Okay, that means now we can have 18 plus the arbitrary constant, 80, e to the negative 5k, because it's after 5 minutes. Yes, just a coincidence that all of the questions have 5 minutes. Just an easy number. And 38, because the temperature of the egg after 5 minutes is 38. Let's solve for k. Now we want to know how much longer will it take for the egg to reach 20. That means 20 equals to our equation. We have the constant, the arbitrary constant and the cooling constant, 0.2770. And now let's subtract 20 minus 18 and divide by 80 equals to that part. And this is 140, 1 over 40, e to the negative 0.77t. And we can see again, 1 over 40 is less than 1, but we can do what we can do. Natural log of 1 over 40 equals to negative 0.277t. And then t equals to natural log of 40 divided by positive 0.2, am I right with this? 77, that's actually correct. And we may leave it like this if it's the test, or we can use the calculator and the answer, I mean the value for this is 13.32 minutes. But do you remember? I said, what is the exact question? I mean, what is the exact correct answer to this question? Because the question is not asking how much time it will take for the egg to reach 20. It's actually saying how much longer. And we know everything, yes? We know everything up to 5 minutes. That means in order to get the correct answer, we have to subtract the 5 minutes. It means how much longer? 8 minutes and 30.32. 8.32 minutes. This is the correct answer, because please remember to subtract 5. That's what I was saying. I hope you had fun with this solution. Okay, you did almost everything on your own. Okay, excellent. You may practice. You have 5 solid questions. If you know how to solve them, you will never make the mistake with the Newton's cooling law. That's the equation, differential equation, and that's the general solution. Okay, thank you.